On a clear night, in a dark enough place, the band of the Milky Way is visible directly overhead. To the naked eye, it looks like a faint river of light, threading from one horizon to the other. What you are actually seeing is the combined glow of hundreds of billions of stars, viewed edge-on from somewhere inside the galaxy's disk. The question of whether anyone else is looking back is one of the oldest questions humans have ever asked. In 2008, a philosopher at Oxford University published a short paper in the MIT Technology Review with a title that read like a provocation. The title was, "Where Are They? Why I Hope the Search for Extraterrestrial Life Finds Nothing." The author was Nick Bostrom, then director of the Future of Humanity Institute at Oxford. The argument the paper made was simple, and once you sit with it, genuinely unsettling. Every Mars rover scraping the Martian soil, every James Webb spectrograph reading the atmospheres of distant exoplanets, every radio dish tracking the sky for an artificial signal, all of it, in Bostrom's view, should fail. Because if any of those searches succeeded, humanity would have the answer to a question that predates science itself. Are we alone in the universe? There is one answer that would be the worst possible news. The silence of the night sky, Bostrom wrote, is golden. We may be alone in this galaxy. We may be alone in the observable universe. And if we are, that is the best news humanity has ever received. This is a video about the silence. The universe is 13.8 billion years old. Compress that span into a single calendar year with the Big Bang on January 1st, and the entire history of recorded human civilization occupies only the final 10 seconds before midnight on December 31st. The Milky Way alone contains roughly 400 billion stars. A 2020 analysis of Kepler mission data, led by Steve Bryson at NASA Ames, estimated that somewhere between 300 million and 2 billion of those stars host a rocky planet in their habitable zone. The galaxy, by every measure we have, should be teeming. So where is everybody? The physicist Enrico Fermi famously asked exactly that, over lunch at the Los Alamos National Laboratory in New Mexico in 1950. He was not the first to ask it. He will not be the last. More than 6 decades of organized listening, from Frank Drake's first radio survey at the Green Bank Observatory in 1960 to the atmospheric biosignature work being done by the James Webb Space Telescope, have produced no signals, no probes, no fossils, no artifacts of any kind. Nothing. Not one confirmed detection of anything beyond our own narrow biological lineage. The silence has a name in the literature. The economist Robin Hanson gave it that name in 1996, in an essay he published online and quietly revised over the following years. He called it the Great Filter. That is the recurring thread of this story. We will return to it again and again, and by the end of this video, you will understand it differently than you do right now. There is one candidate for where the filter lives that the popular telling of this story almost always skips. A single biological event on this planet, roughly 2 billion years ago, that may not have happened anywhere else in the galaxy. Deeper into this video, you will know what it was and why your existence depends on it. But first, if the deep silence between the stars keeps you company at night, you are in the right place. Subscribe and settle in. What Bostrom argued in his 2008 paper and what Hanson formalized in his 96 essay point at the same uncomfortable conclusion. Somewhere in the long chain of events between a sterile rocky planet and a civilization that fills its galaxy, there is a step that almost nothing survives. The question is where. The question is whether the step is behind us or ahead. And there is a particular kind of evidence that would tell us which. Evidence we are actively searching for, with billions of dollars of equipment, on a planet one orbit over from our own. The strangest part of Bostrom's argument is this. If the rovers crawling across Mars find what every astrobiologist on Earth is hoping they find, even a single fossilized microbe in a billion-year-old rock, It will be the worst news humanity has ever received. We will get to exactly why. To understand why the silence matters, you have to understand what it was supposed to sound like. In the autumn of 1961, an American astronomer named Frank Drake organized the first scientific meeting ever held on the question of extraterrestrial intelligence. The conference was held at the National Radio Astronomy Observatory in Greenbank, West Virginia. It was a small gathering by the standards of modern science. Roughly a dozen people attended in person. Drake had invented a formula in the weeks before the meeting, not because he expected to calculate the answer, but because he needed a structure for the conversation, something to organize the agenda. The formula has since become the second most famous equation in science, after Einstein's mass-energy equivalence. It is called the Drake equation. The attendees were a strange mix of disciplines. Drake himself was an astronomer. Philip Morrison, a physicist from MIT, was there for theoretical depth. The young Carl Sagan, then 27 years old and still years away from public fame, was there as the field's most articulate communicator. The biochemist Melvin Calvin attended, and partway through the meeting was pulled out of the room by a telephone call informing him that he had just been awarded the Nobel Prize in Chemistry. The biologist Joshua Lederberg, who had himself won a Nobel 3 years earlier, attended for the biological side of the question. A radio engineer named Barney Oliver, who had self-invited himself to the meeting after hearing about it, attended for the engineering reality of how signals would actually be detected. There were others. The total was somewhere between 10 and 12 people, depending on which historian you ask. They had 3 days. The question was simple. If there are other civilizations in this galaxy, how many of them are there, and what would it take to find them? Drake wrote his equation on the chalkboard in the conference room. The equation, written out, looks like this. The number of detectable civilizations in our galaxy, called N, equals the rate of star formation in the galaxy, multiplied by the fraction of stars that have planets, multiplied by the average number of planets per system that could in principle support life, multiplied by the fraction of those planets where life actually starts, multiplied by the fraction of those biospheres where life develops into intelligence, multiplied by the fraction of intelligent civilizations that develop technology capable of releasing detectable signals, multiplied by the average length of time over which such civilizations remain detectable. 7 factors. 1 result, the Drake equation. In 1961, the room had hard numbers for exactly one of those factors. The rate of star formation in the Milky Way had been measured. The rest were guesses, defended with varying degrees of confidence. Some were guesses about astronomy. Some were guesses about biology. Some were guesses about the long-term behavior of intelligent civilizations, which is to say, guesses about a question humanity has no experience with. But the structure was real. The equation made the unknowns visible. It turned a vague, metaphysical question into a chain of factors that could, in principle, each be measured separately. The meeting set the field's agenda for the next 60 years. I want to walk through what has happened to those 7 factors since. The first factor, the rate of star formation, has been refined from rough guesses to well-constrained measurement. The Milky Way produces, on average, between 1 and 3 new stars per year. The number sounds modest until you remember that the galaxy has been doing it for 13 billion years. The cumulative result is the 400 billion stars in our galaxy. Of those, around 7% are similar to our Sun in mass, temperature, and lifespan. That gives us approximately 28 billion Sun-like stars in the Milky Way alone. To put 28 billion in human terms, if every Sun-like star were a grain of sand, you would have enough sand to fill a small swimming pool. And that is just one galaxy out of the roughly 2 trillion galaxies in the observable universe. The second factor, the fraction of stars with planets, is where the deepest revision has happened since the Green Bank meeting. In 1961, no exoplanet had been confirmed. Drake guessed the fraction was around 1/5. He was being conservative. The first confirmed exoplanet was discovered in 1995, orbiting a sun-like star called 51 Pegasi by the Swiss astronomers Michel Mayer and Didier Queloz. Since then, more than 5,000 exoplanets have been catalogued, more than half of them detected by the Kepler Space Telescope between 2009 and 2018. The data has narrowed the second factor's value dramatically. We now believe that essentially every star in the galaxy hosts at least one planet. The number is not 1 in 5. The number is 1 in 1. The third factor, the average number of planets in each system that could in principle support life, has also been revised upward. In 1961, Drake assumed it was around 1. Modern Kepler analyses, including the 2020 paper led by Steve Bryson at NASA Ames, suggest that around half of all sun-like stars host at least one rocky planet in their habitable zone. The galaxy contains, by these estimates, between 300 million and 2 billion potentially habitable rocky worlds. By every estimate, the galaxy is rich in real estate. Earth is not a special place. There are billions of equivalents. The first three factors of Drake's equation, taken together, give a number that requires explanation. Roughly 1 billion habitable worlds in our galaxy. Roughly 2 trillion galaxies in the observable universe. The number of potentially habitable rocky planets in the cosmos we can see is greater than the total number of grains of sand on every beach and in every desert on Earth, by many orders of magnitude. The supply of biological real estate is not the bottleneck. The supply is essentially unlimited. The remaining 4 factors of the Drake equation are the difficult ones. The fraction of habitable planets where life actually emerges. The fraction of biospheres that develop into intelligence. The fraction of intelligent species that produce detectable technology. The average length of time those technological civilizations remain detectable. Each of these has been the subject of decades of debate. Each, depending on which scientist you ask, could be 1, or could be 1 in 10,000, or could be smaller still. The math of the equation is exquisitely sensitive to the values of these 4 factors. Change one of them by a factor of 10, and the conclusion shifts by an order of magnitude. In 1961, the Green Bank attendees were optimistic. The consensus that emerged from their 3 days of discussion was that the number of detectable civilizations in the Milky Way alone was somewhere between 1,000 and 100 million. Carl Sagan and the optimists landed near the upper end of that range. The more conservative attendees, including Drake himself, landed in the middle. Nobody at the meeting argued the number was small. Nobody argued the number was 0. The room agreed, in its 3 days of conversation, that the galaxy was probably full of life, and that the only question was how to find it. The Green Bank meeting set the conversation. The next major chapter in the field's history was an attempt to put steel and concrete behind it. In 1971, NASA commissioned a feasibility study for a dedicated search telescope unlike anything ever built. The project was called Cyclops. The study was led by Barney Oliver, the same Barney Oliver who had attended the Green Bank meeting as a self-invited radio engineer, and by John Billingham at the NASA Ames Research Center. It ran for the entire summer of 1971 at Stanford University. Roughly 30 engineers and scientists worked through the design across 3 months. The proposal was audacious. A phased array of 1,500 radio dishes, each 100 meters across, arranged in a hexagonal grid covering 25 square kilometers in the Arizona desert. Working together, the dishes would form a single virtual telescope with the equivalent aperture of a dish more than 3 kilometers wide. The array would have been capable of detecting Earth-equivalent transmitters from any of the nearest 1,000 sun-like stars, and Earth-level radar leakage from the nearest 100. It would have been, by orders of magnitude, the most sensitive radio telescope ever built. The cost estimate, in 1971 dollars, was around $10 billion. In 2025 dollars, more than $70 billion. The Cyclops report, formerly titled Project Cyclops, a design study of a system for detecting extraterrestrial intelligent life, was published in 1973. It became the foundational document for every serious SETI proposal that followed. Every modern array, every funding pitch, every technical paper on techno-signature detection traces some of its lineage back to the Cyclops study. Congress killed the project. Funding was never allocated. The array was never built. The decision was, in retrospect, a turning point in the field. Cyclops would have either found something within a few decades of operation, or it would have demonstrated that the silence extended much further than even the pessimists believed. We will never know which. In the absence of Cyclops, SETI continued at a smaller scale. The field became dependent on time-sharing arrangements with telescopes built for other purposes. The Arecibo dish, the Greenbank telescope, the Very Large Array in New Mexico. Every observation campaign had to compete with mainstream radio astronomy for telescope hours. The search has been, ever since, opportunistic rather than systematic. Carl Sagan, by then a professor at Cornell and the most public face of American science, lobbied throughout the 1970s and 80s for a dedicated SETI program. He founded the Planetary Society in 1980, along with Bruce Murray and Lewis Friedman, in part to fund SETI work that government agencies refused to support. His 1985 novel Contact, later adapted into the 1997 film of the same name, made the question of extraterrestrial intelligence familiar to millions of people who had never thought about it. Sagan died in 1996, the same year Robin Hanson published The Great Filter Essay. He did not live to see the field's reshaping by the Kepler mission, or the discovery of the first exoplanets in their habitable zones, or the development of biosignature spectroscopy that would eventually be turned on K2-18b. What Sagan and the Cyclops era left behind, by the time of his death, was a question that had grown sharper rather than dimmer. The catalogues of known habitable worlds had grown by orders of magnitude, and the silence had only gotten louder. The optimism of 1961 did not last. In 1975, an astronomer named Michael Hart published a paper in the Quarterly Journal of the Royal Astronomical Society titled An Explanation for the Absence of Extraterrestrials on Earth. Hart's argument was simple and devastating. If the galaxy is as full of life as the Drake equation suggests, and if even a small fraction of those civilizations develop interstellar travel, then the galaxy should already be colonized. Not in the future, now. Hart's calculation, a civilization expanding outward at 1% the speed of light, a velocity well within the bounds of known physics, would colonize every habitable system in the Milky Way in roughly 10 million years. The galaxy is approximately 13 billion years old. There has been time for any civilization that ever arose to have spread, and to have continued spreading more than 1,000 times over. Hart's conclusion: if there are no signs of colonization, there are no colonizers. The galaxy is empty. The paper was controversial. Frank Tipler, a mathematical physicist at Tulane University, extended Hart's argument in 1980 in a paper titled Extraterrestrial Intelligent Beings Do Not Exist. Tipler argued that if any civilization at any point in the history of the Milky Way had developed self-replicating probes, robotic spacecraft capable of building copies of themselves from raw materials in each new star system, then the galaxy would have been saturated with such probes within a few million years of the first one. We see no probes. We see no engineered structures around nearby stars. We see no waste heat from advanced civilizations operating Dyson spheres. We see no evidence of any technological activity anywhere in our cosmic neighborhood. By Tipler's logic, this means no such activity has ever occurred. This was a profound shift in the field. Within 15 years of the Greenbank meeting, 2 formal papers in respected journals had argued that the expected outcome of the Drake equation, a galaxy full of detectable civilizations, was empirically wrong. The galaxy was not full. The galaxy was, as far as anyone could tell, totally empty. Either the math was wrong, or one of the factors in the Drake equation was being radically overestimated, or something was preventing intelligent civilizations from spreading across galactic distances, or all three. The decades since Hart and Tipler's papers have produced no evidence to contradict them. The exoplanet revolution has confirmed that the galaxy is full of potentially habitable worlds, not less full. The Kepler mission has driven the numbers up, not down. Each new finding has made the silence more anomalous, not less. The first factor of the Drake equation, star formation, is well constrained. The second factor, the fraction of stars with planets, is approximately 1. The third factor, the fraction of habitable planets, is high. The math with these factors plugged in says the galaxy should be loud. The galaxy is silent. Whatever explanation we accept for that silence has to account for not just the absence of communication, but the absence of evidence of any kind. No signals, no probes, no mega engineering, nothing that can be detected, measured, or photographed from any of our observatories. 6 decades of looking, and the universe has refused to wave back. There is a problem in the consensus. Something is missing from the picture. Either the Drake equation has been wrong about a parameter, or the math is being undone by a process nobody anticipated. This was the loose thread. By the late 1970s, the field had a name for the problem. It was called the Fermi paradox. But there is something the consensus could never quite explain, even as it was forming. The Fermi paradox did not appear out of nowhere in the 1970s. The shape of the problem was present at the very first moment anyone seriously asked the question. The shape was present at a lunch table in New Mexico on a summer day in 1950. The setting, Los Alamos National Laboratory, the secret facility in northern New Mexico that had built the first atomic bombs 5 years earlier. The laboratory was, in 1950, in the middle of a frantic effort to build the world's first thermonuclear weapon, a project triggered by the Soviet Union's nuclear test in August of 1949. The most accomplished physicists alive were rotating through Los Alamos on extended visits. One of them was Enrico Fermi. Fermi was, by then, one of the most respected physicists in the world. He had won the Nobel Prize in 1938 for his work on induced radioactivity. He had led the team at the University of Chicago that built the world's first nuclear reactor on December 2, 1942, in a converted squash court underneath the football stadium. He was 49 years old in 1950 and at the height of his powers. One day in the summer of that year, Fermi was walking from his lodgings to the Fuller Lodge dining hall at Los Alamos in the company of 3 colleagues. The colleagues were Edward Teller, the Hungarian-born physicist who would later be called the father of the hydrogen bomb; Emil Konopinski, a Polish-American nuclear theorist; and Herbert York, a younger physicist who would go on to direct the Lawrence Livermore National Laboratory. The walk was perhaps 10 minutes. On the way, the conversation turned to a topic that had been in the newspapers for weeks: flying saucers. The summer of 1950 saw a wave of UFO sightings across the United States, and the press was full of speculation. There was even a New Yorker cartoon, published on May 20th of 1950, that had struck Fermi as particularly funny. The cartoon depicted little green men carrying away New York City trash cans, which had been disappearing from the city around the same time as the UFO sightings. The premise was that one extraterrestrial phenomenon explained both unrelated mysteries. The 4 physicists walked and discussed the sources. They considered, in the half-serious way physicists do, whether such craft could exceed the speed of light. They made bets. They sketched calculations on napkins. The conversation was relaxed, the way a long overdue lunch ought to be. By the time they sat down at their table in the Fuller Lodge, the conversation had drifted to other topics. The saucer discussion was, for the others, finished. Fermi, apparently, had not finished thinking about it. In the middle of an unrelated discussion, Edward Teller would later recall, Fermi suddenly looked up and asked, with the abruptness for which he was famous, the question: "Where is everybody?" The other 3 immediately understood what he meant. The pause at the table was, by Teller's later recollection, brief but absolute. The question hung in the air. Nobody had a good answer. The exchange was documented years later by the Los Alamos historian Eric Jones, who tracked down the surviving witnesses and reconstructed the conversation from their memories. Jones published his findings in a Los Alamos report in 1985. The Fermi question, "Where is everybody?" is recorded in his report, essentially as Teller, and the others remembered it. What did Fermi mean? His back-of-the-envelope reasoning on the walk over had been roughly this. The Milky Way contains hundreds of billions of stars. Many of them are billions of years older than our Sun. If even a small fraction of those stars produce civilizations, and if even a small fraction of those civilizations developed interstellar travel, then the galaxy should have been colonized long before the Earth even formed. There should be settlers in our solar system. There should be derelict probes orbiting in our outer system. There should be radio chatter audible to our most basic receivers. There is none. And so, where is everybody? Fermi died of stomach cancer 4 years later, in 1954. He was 53 years old. He never published a paper on the question he had asked over lunch. He never returned to it formally in print. The question survived only in the memories of the men at the table. It would be 25 years before the question received its formal treatment in the scientific literature. The treatment, when it arrived, came from Michael Hart and from Frank Tipler, the same papers we walked through earlier. Hart and Tipler quoted Fermi's question and credited him with first asking it. The phrase Fermi paradox became standard. The paradox is this. The math says the galaxy should be full of civilizations. The observations say the galaxy is empty. Something has to give. By the time Hart and Tipler published, organized listening for alien signals had been underway for 15 years. The listening had started in April of 1960, when Frank Drake, the same astronomer who would later organize the Green Bank meeting, pointed an 85-foot radio telescope at two nearby sun-like stars. The stars were Tau Ceti, 11.9 light-years away, and Epsilon Eridani, 10.5 light-years away. Drake listened on the hydrogen frequency, 1420.4 MHz, on the theory that any technological civilization interested in interstellar communication would choose a frequency that any other technological civilization would also recognize as significant. He listened for around 200 hours over the spring and summer of 1960. He called the project Ozma, after the queen of L. Frank Baum's fictional Land of Oz. He found nothing. The two stars were silent. 4 years after Project Ozma, in 1964, the Soviet astrophysicist Nikolai Kardashev published a paper that quietly defined what SETI was actually looking for. Kardashev was a graduate student of Iosif Shklovsky, the most influential Soviet astronomer working on the question of extraterrestrial intelligence at the time. The paper, titled Transmission of Information by Extraterrestrial Civilizations, proposed a scheme for ranking civilizations by the amount of energy they were capable of capturing and using. Kardashev described 3 types. A Type 1 civilization would be capable of harvesting all the energy that falls on its home planet from its parent star. Earth, by his 1964 definition, was approaching Type 1 but had not yet reached it. A Type 2 civilization would be capable of harvesting the total energy output of its parent star, the scale at which a Dyson sphere becomes a plausible construction. A Type 3 civilization would be capable of harvesting the energy of an entire galaxy. The differences in scale between the 3 types are enormous. A Type 2 civilization commands roughly 10 billion times more energy than a Type 1. A Type 3 commands roughly 10 billion times more than a Type 2. To put that in human terms, the jump from Type 1 to Type 2 is the difference between every power plant humanity has ever built combined, and the entire luminous output of a star radiating in every direction at once. The scheme mattered for SETI because it defined what would actually be detectable across interstellar distances. A Type 1 civilization is only marginally visible from outside its own solar system. A Type 2 civilization produces a clear infrared signature from its dimmed star and its waste heat. A Type 3 would, in principle, light up its host galaxy in ways that ought to be obvious to any observer with a decent telescope. The galaxy, when astronomers looked, contained no Type 3 civilizations. The galaxies surveyed by infrared satellites in the decades after Kardashev's paper contained no Type 2 structures. The targets near Earth produced no Type 1 radio chatter. The Kardashev scale, in its strict form, had failed to find any of its three categories. Project Ozma is now regarded as the founding event of SETI, the search for extraterrestrial intelligence. In the 6 decades since, hundreds of observation campaigns have been mounted on hundreds of stars across dozens of frequency bands. The campaigns have ranged from a few hours to multi-year systematic surveys. The instrumentation has improved by orders of magnitude. The amount of sky covered has expanded from 2 stars to the entire visible galaxy. The result, across every campaign, every band, and every star, has been the same: silence. There has been one famous exception to the silence, one signal that briefly made the SETI community wonder if the wait might be ending. On the night of August 15, 1977, the Big Ear radio telescope at Ohio State University picked up a narrowband signal coming from the direction of the constellation Sagittarius. The signal was strong. It lasted 72 seconds, the exact length of time the telescope's fixed dish could hold a single patch of sky in view as the Earth rotated. It was tuned to 1,420 megahertz, the same hydrogen line frequency Frank Drake had used at Project Ozma 17 years earlier. A few days later, the volunteer astronomer Jerry Eman was reviewing the night's data line by line on a roll of printer paper. He saw the signal's intensity sequence written in the observatory's coded shorthand as the string 6EQUJ5. He drew a circle around it in red ink and wrote, in the margin of the printout, the single word, wow. The wow signal, as it came to be known, was the strongest candidate techno-signature SETI had ever produced. Astronomers immediately scheduled follow-up observations of the same patch of sky. The Big Ear itself was re-aimed at the source the following night. The Very Large Array, the Arecibo dish, the Greenbank telescope, and dozens of other instruments across decades returned to that specific spot in Sagittarius and listened. Nothing came back. The signal never repeated. In 2024, a team led by the astrobiologist Abel Mendez at the University of Puerto Rico at Arecibo published a reanalysis of the original Big Ear data. Their proposal was that the WOW signal had been a naturally occurring maser, a stimulated emission of microwave radiation produced when a passing cloud of cold hydrogen gas was briefly excited by the radiation from a distant astrophysical source. A transient brightening of that kind would explain the signal's properties and its failure to repeat. The most famous candidate signal in the history of SETI may have been, in the end, a passing molecular cloud. The search has not been limited to radio. In the 1970s, the search expanded to optical wavelengths, looking for short, intense laser pulses of the kind a transmitting civilization might use to send a signal across interstellar distances. Optical SETI, as the field is called, has its own dedicated instruments, including the automated planet finder at Lick Observatory in California and the dedicated optical SETI program at Harvard University. Decades of looking. No confirmed pulse from any star on any wavelength, ever. The search has not been limited to artificial signals either. In the 1960s, the physicist Freeman Dyson proposed that an advanced civilization, having converted its home planet into raw material for orbital habitats, might surround its star with a swarm of solar collectors. The waste heat from such a structure, called a Dyson sphere, would be detectable as an excess of infrared radiation from a star that otherwise looked normal. The hunt for Dyson sphere infrared signatures has been ongoing since the 1960s. No such structures have been detected anywhere in the galaxy. Nothing absorbs starlight and re-radiates it in a pattern consistent with engineering. Every star within our reach appears to be doing what stars naturally do, and nothing more. The search has not been limited to the local neighborhood. In 2015, the Russian-Israeli investor Yuri Milner announced a $100 million 10-year SETI initiative called Breakthrough Listen. The project, hosted at the University of California at Berkeley, combined radio observations from the Green Bank Telescope and the Parkes Observatory in Australia with optical observations from the automated planet finder at Lick. The mandate was to perform the most thorough techno-signature search in history. The targets included the nearest 1 million stars to Earth, the entire galactic plane, and the centers of the 100 nearest galaxies. The project produced petabytes of data, scanned billions of frequency channels, and applied machine learning to filter out terrestrial radio interference. A decade in, Breakthrough Listen has nothing to show. Not one confirmed candidate signal in petabytes of data. The most recent high-profile Breakthrough Listen observation was conducted on December 18, 2025. The target was an unusual one. An interstellar object, designated 3I Atlas, had been discovered in July of that year as it passed through the inner solar system. It was the third interstellar object ever observed, after Oumuamua in 2017 and Borisov in 2019. Some astronomers, most prominently the Harvard physicist Avi Loeb, suggested that the object's trajectory and behavior warranted serious investigation as a potential techno-signature. On the day before 3I Atlas made its closest approach to Earth, Breakthrough Listen used the 100-meter Robert C. Byrd Green Bank Telescope to scan the object across 4 radio bands, from 1 to 12 gigahertz. The observation lasted 30 minutes. The sensitivity threshold was extreme. The system could have detected an artificial transmitter as faint as 100 milliwatts, about the power of a low-end consumer device, broadcasting from the object's location. The result was published a week later in a research note. No candidate signals were detected. The object, like every other target SETI has ever examined, was silent. 2 complementary lines of work developed alongside the listening campaigns. The first was the question of whether humans should be transmitting outward, not just listening inward. In 1974, on November 16th, a ceremony was held to mark the upgrade of the Arecibo radio telescope in Puerto Rico, at the time the largest single-aperture radio telescope in the world. Frank Drake, by then the director of the Arecibo Observatory, had designed a transmission to be broadcast during the ceremony. The transmission was 3 minutes long. It was aimed at a globular star cluster called M13, 25,000 light-years from Earth, chosen because it contained roughly 300,000 stars in a tight gravitationally bound group. Any reply would take 50,000 years to arrive, round trip. But the broadcast was less about getting an answer than about doing the thing, proving that an interstellar message was technically possible. The signal contained 1,679 binary digits arranged in a grid 23 columns wide and 73 rows tall. The grid encoded the numbers 1 through 10, the atomic numbers of the elements that make up DNA, the chemical structure of the DNA nucleotides, the shape of the double helix, a human figure, the size of the human species in 1974, at just over 4 billion, the structure of our solar system with Earth highlighted, and a picture of the Arecibo dish itself. It was, in essence, a postcard with humanity's address and biology on it. The message was sent. The dish was then re-aimed. The transmission was never repeated. The signal continues outward at the speed of light, a thin slice of radio energy now more than 50 light-years from Earth. 3 years later, in 1977, NASA launched the Voyager 1 and Voyager 2 spacecraft on a tour of the outer solar system. Mounted on the side of each spacecraft was a gold-plated copper phonograph record. The records were the work of a committee chaired by Carl Sagan, with contributions from Frank Drake, the writer Anne Druyan, who would later become Sagan's wife, and the artist John Lomberg. Each record contained 115 images, greetings in 55 languages, including ancient Akkadian, 12 minutes of natural sounds from Earth, and 90 minutes of music ranging from Bach to Chuck Berry to Senegalese percussion. The records were designed to last 1 billion years in the radiation environment of deep space. 1 billion years is longer than complex multicellular life has existed on Earth. The Voyagers crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar space, in 2012 and 2018 respectively. They are now drifting outward, still carrying their records. They will, in roughly 40,000 years, pass within 1.5 light-years of the star Gliese 445 in the constellation Camelopardalis. No one will be there to greet them. The decision to broadcast at all, rather than just to listen, has remained contested in the field. The practice of intentional transmission is called messaging extraterrestrial intelligence, or METI. Critics, including the physicist Stephen Hawking before his death in 2018, argued that announcing humanity's existence to any potentially hostile civilization within range was, on balance, unwise. Defenders, including Frank Drake, argued that any civilization advanced enough to detect us probably already had. Our radio leakage has been expanding outward at the speed of light for more than a century. The argument has been ever since philosophical rather than scientific. There is no formal international policy on whether to transmit. The second complementary line of work was the construction of dedicated equipment. By the early 2000s, the SETI community had grown weary of competing for telescope time on instruments built for other purposes. In 2004, the SETI Institute partnered with the University of California at Berkeley to build a dedicated array at Hat Creek Observatory in Northern California, 350 kilometers north of San Francisco. The array was funded primarily by Paul Allen, the co-founder of Microsoft, who pledged $30 million toward its construction. It was named the Allen Telescope Array. The array, when completed in 2007, consisted of 42 6-meter dishes operating in concert. It was designed to grow to 350 dishes eventually. The growth never happened. In 2011, the SETI Institute lost the operating funding that had kept the array running, and the entire facility was placed in hibernation. It was eventually revived through a combination of US Air Force interest in space surveillance and renewed private donations, and the array is operational again, though at a fraction of its originally intended capacity. The story of the Allen Telescope Array is, in some sense, the story of every dedicated SETI project that has ever existed. Ambitious initial vision, partial construction, funding crisis, survival in reduced form. The field has never had the resources its proponents argued were necessary. And in every form the search has taken. Opportunistic listening on borrowed dishes, dedicated arrays in Northern California, transmitted postcards aimed at distant globular clusters, gold records flying outward on Voyager spacecraft. The dishes have come back empty. Nothing has answered. This is the part that the popular accounts of SETI tend to skip. The popular accounts describe each null result as a setback. Each new generation of equipment is introduced as the one that might finally find a signal. The narrative is one of perpetual approach. We are getting closer. Soon, perhaps, we will hear something. The unpopular interpretation is that the silence is the answer, not a failed measurement, a successful one. The dish has been picking up exactly what is there to pick up, and whatever process is producing the complete absence of a signal has been producing it consistently across every star, every frequency, every observation, for as long as humanity has been listening. What this means, taken together, is that the silence is not a problem of insufficient effort. The search has been mounted for 65 years, with growing sophistication, across multiple wavelengths, across multiple kinds of expected signature, across both nearby stars and distant galaxies. The total area surveyed is vast. The total duration of cumulative listening, measured in radio telescope hours, exceeds 100,000. And the result, across every campaign, every method, every instrument, has been the same. The galaxy is silent. Our local universe is silent. The signal humanity has been listening for is not arriving. The natural explanation, and the one most popular among optimistic astronomers, is that we have not yet listened in the right way, or for long enough, or at the right frequencies. The natural explanation is that the search is still in its early stages, and that the right discovery is still ahead. The alternative explanation is the one Robin Hanson formalized in 1996. There is nothing to find. The great filter is, in Hanson's framing, whatever combination of events makes the math of the Drake equation produce a number close to zero when you run the calculation honestly. Some specific step, somewhere between sterile rocky planets and galaxy-spanning civilizations, is so improbable that the universe almost never produces a successful crossing. The math says we should be common. The observations say we are alone. The filter is the reconciliation between the two. The question that follows is the dangerous one. Where is the filter? Behind us, in our biological past? Or ahead of us, in our technological future? Because that question, for the first time in this story, makes a prediction about something we can check, not by listening to the stars, by looking at the dirt. The math had to work somehow. Here is where the theorists started looking. Robin Hanson's 1996 essay, written as a draft and quietly revised over the following years, broke the problem into 9 specific transitions. Hanson called them the 9 steps. Each step was an evolutionary or technological transition that any civilization would have to cross in order to become detectable across interstellar distances. The combined probability of crossing all 9 had to be small enough to explain the observed silence. Or, said differently, the probability of failing at one of the 9 had to be large enough that almost nothing made it through. Hanson's 9 steps run like this: the right star system, replicating molecules; simple, single-celled life; complex, single-celled life; sexual reproduction; multicellular life; tool-using animals with large brains; the current human stage, with industrial technology; interstellar colonization, or the equivalent technological footprint that would be detectable from elsewhere in the galaxy. These 9 steps can be thought of as gates. A planet on which life arises but does not develop complex single cells fails at gate 4. A planet on which complex single cells exist but never develop multicellular organisms fails at gate 6. A planet on which intelligent technological species arise but destroy themselves before becoming detectable fails at gate 9. The filter, in Hanson's framing, is whichever combination of gates is acting as the bottleneck. Most planets that make it to one gate do not make it to the next. Eventually, almost no planets make it to gate 9. The interesting question is, which gate is the worst? Which gate fails the most often? Because that gate, wherever it lives, determines what kind of universe we live in. The first candidate is abiogenesis, the transition from non-living chemistry to self-replicating life. For most of human history, the consensus assumption was that abiogenesis was the bottleneck. Life was thought to be staggeringly improbable. The chemistry was complex. The conditions had to be precise. The probability of going from a sterile rock to a self-replicating molecule was vanishingly small, and most planets, even with billions of years of opportunity, never crossed the threshold. Then the geology started disagreeing. In September of 2016, a team led by the Australian geologist Alan Nutman of the University of Wollongong published a paper in the journal Nature reporting the discovery of 3.7 billion-year-old fossilized microbial mats in a remote location on the western edge of Greenland. The site is called the Isua Greenstone Belt. The rocks are among the oldest sedimentary deposits ever found on Earth. The structures the team identified, called stromatolites, are layered formations produced by colonies of microscopic organisms that lived in shallow water and built up mineral mats over time. The age of the fossils placed them at a stunning early position in Earth's history. Earth itself formed roughly 4.5 billion years ago. The early Earth was sterilized by ongoing asteroid impacts during a period called the Late Heavy Bombardment, which ended around 4 billion years ago. The Greenland stromatolites are dated to 3.7 billion years ago. That means life on Earth, complex enough to form colonies and leave fossil mats, existed within 300 million years of the planet becoming habitable. 300 million years is a long time in human terms, roughly 60,000 times longer than the entire span of recorded human history. But in the geological history of a planet, it is the blink of an eye. In 2017, a separate team led by Matthew Dodd at University College London announced the discovery of even older fossil evidence. Hematite tubes from hydrothermal vent precipitates in the Nouveau-Guittuc greenstone belt in northern Quebec, dated to at least 3.77 billion years old, and possibly as much as 4.28 billion years old. If the older end of that range is correct, life on Earth predates the end of the Late Heavy Bombardment. Life would have started while the planet was still being routinely sterilized. The implication for the Great Filter is direct. If life arose on Earth essentially as fast as it was thermodynamically possible for it to arise, within a few 100 million years of the planet's surface becoming stable, then abiogenesis cannot be the bottleneck the filter requires. Whatever process produces self-replicating chemistry, it appears to be common, not rare. The chemistry, given any reasonable habitable planet, seems to want to assemble itself into life. The first gate in Hanson's 9 steps may be the easiest one to cross. This is bad news, in a specific sense. If gate 1 is easy, the filter must live at one of the later gates. The harder gates are ahead of life, not behind it. And several of those later gates lie ahead of where humanity currently sits. Before we walk through the rest of Hanson's gates, there is a complementary framework worth pausing on. The framework was developed by a paleontologist and an astronomer working together and published in 2000 under a title that captured the entire argument in 2 words. Peter Ward, a paleontologist at the University of Washington, and Donald Brownlee, an astronomer at the same university, published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. The book offered an alternative to Hanson's framing of the question. Where Hanson asked which single gate was the bottleneck, Ward and Brownlee asked which conditions, taken together, were necessary to produce a planet capable of supporting complex life at all. Their answer was a long list. Each item on the list was a condition that, on Earth, had quietly contributed to producing the long-lived, stable environment in which complex biology had become possible. Most popular discussions of habitable planets focus on a small subset of these conditions: the right temperature for liquid water, the right kind of star to orbit, the right distance from that star, and the right atmospheric pressure. Ward and Brownlee argued that these were the easy ones. The hard conditions, the ones that almost no one talked about, were the conditions that had to compound over billions of years to produce a biosphere that did not stall at the bacterial stage. Plate tectonics, for example. The active recycling of a planet's crust regulates atmospheric carbon dioxide across geological time, replenishes ocean chemistry through volcanic outgassing, and helps sustain a magnetic field that shields the surface from solar wind. Most rocky planets do not have active plate tectonics. The ones that start with them typically lose them within the first billion years, as their internal heat dissipates. Mars lost its plate tectonics around 4 billion years ago, which is why its atmosphere has been steadily stripped away ever since. Venus may never have had active plate tectonics at all. The combination of size, internal heat, water content, and chemical composition required to sustain plate tectonics across billions of years is narrower than the popular telling of habitable planet science suggests. A large, stabilizing moon. Earth's moon is unusually large for a terrestrial planet. It is roughly 1/4 the diameter of Earth itself, the largest moon-to-planet ratio of any major planet in the solar system. The moon stabilizes Earth's axial tilt, which would otherwise wander chaotically under gravitational perturbations from Jupiter and the other planets. A wandering axial tilt produces wildly variable climates across geological time, which makes long-term biological evolution difficult. The Moon is believed to have formed from a single giant impact between the proto-Earth and a Mars-sized body roughly 4.5 billion years ago. The impact had to be just energetic enough to produce a stable companion, but not so energetic that it destroyed the planet entirely. The probability of such a collision occurring at the right angle and the right velocity is, by current estimates, small. A gas giant protector. Jupiter has been called the inner solar system's vacuum cleaner. Its enormous gravity captures or deflects most of the asteroids and comets that would otherwise enter the inner solar system. Without Jupiter, the rate of catastrophic impacts on Earth would be perhaps 1,000 times higher than it has been. Some impacts that have hit Earth over the last several hundred million years would have been many times worse without Jupiter screening the worst out. A planetary system without an appropriately placed gas giant has, in this argument, a much harder time keeping its inner planets habitable for the deep timescales complex life requires. The right location in the galaxy, too close to the galactic center, and stellar density makes nearby supernovas dangerously frequent. Gamma-ray bursts and other energetic events repeatedly sterilize whatever life forms there. Too far from the center, and the heavy elements necessary for rocky planet formation become too scarce to produce Earth-like worlds. Earth sits in what astronomers now call the galactic habitable zone, a narrow ring of the disk where the local density of supernovae is low, but heavy element abundance is still high enough. The width of this ring is, by some estimates, a few thousand light-years out of a galaxy, roughly 100,000 light-years across. The right kind of star, long-lived, stable, and not too magnetically active. Sun-like G-type stars meet these criteria, but most stars in the galaxy are not Sun-like. Roughly 70% of the galaxy's stellar population are smaller M-type red dwarfs, which emit much of their energy in ultraviolet flares that can strip atmospheres from any planets close enough to be in the habitable zone. Planets around red dwarfs are also tidally locked, with one side perpetually facing the star and the other in permanent darkness. The fraction of stars genuinely friendly to long-term Earth-like biology is, in the rare Earth framing, perhaps 1 in 10 of the galaxy's total. Each of these conditions, taken individually, is not strictly improbable. Plate tectonics happens. Large moons form. Gas giants are common. Habitable galactic zones exist. The right kind of star exists. The improbability is in getting all of them at the same time, on the same planet, sustained for billions of years. Ward and Brownlee's calculation, multiplying the probabilities of each condition together, produced a number small enough that complex life would emerge in only a tiny fraction of the planetary systems in the galaxy. Their estimate was conservative. They did not claim humanity was unique in the universe. They claimed only that the kind of multi-billion-year stability required for complex biology to develop was, by every available measure, rare. The rare Earth hypothesis and Hanson's great filter framework are not in opposition, they are complementary. Hanson's framework asks which single gate is the worst. Rare Earth answers that many of the gates may be individually unlikely, and that the combined improbability of clearing all of them is what accounts for the silence. The frameworks merge naturally when you ask the next question. Within the compounded picture, Rare Earth describes which of Hanson's individual gates is the hardest. The answer biologists keep returning to when they look at the geological record and the biochemistry of cells is the one we are about to walk through. Within Hanson's 9-step framework, the second candidate is the transition from simple, single-celled life to complex, single-celled life, from prokaryotes to eukaryotes, from cells without internal structure to cells with mitochondria, nuclei, and organized internal compartments. This transition happened on Earth only once that we know of, roughly 2 billion years ago. It happened slowly, from the appearance of the first prokaryotic life around 3.7 billion years ago, to the appearance of the first eukaryotic cell around 2 billion years ago. Almost 2 billion years passed. Half the history of life on Earth was spent at the prokaryotic stage. 2 billion years of bacteria, and nothing more complex. The transition itself, when it finally occurred, was a one-off event. The leading theory, now widely accepted, is that the first eukaryotic cell was created by an unlikely accident. One archaeal cell engulfed a bacterial cell, did not digest it, and the two became permanently fused. The engulfed bacterium became the ancestor of every mitochondrion in every eukaryotic cell that has ever lived. Every plant, every animal, every fungus, every protozoan, every breathing listener of this video. All of us descend from that single cellular accident, an event with no known equivalent across the entire 4 billion year history of life on Earth. The British biochemist Nick Lane has spent his career working out the energetic mathematics behind why this transition was so hard. The argument, simplified, is this: bacterial cells are limited in genomic complexity by their energy budget. A bacterium produces its energy at the cell membrane, and the surface to volume ratio of a bacterium puts a hard cap on how much genetic material it can support. The only way around the limit is to internalize the energy production, to put the membranes inside the cell in dedicated organelles so that a much larger genome can be supported by a much greater interior surface area. That is exactly what mitochondria do. They are internalized power plants, dedicated membranes for ATP production that allow eukaryotic cells to support genomes 10 to 100 times larger than any prokaryote can manage. Without that internalization, complex life cannot exist. Without mitochondria, the energy budget is too small. The cell hits a wall. Lane's conclusion is unsettling. The eukaryotic transition, on this view, is not a probable outcome of bacterial evolution. It is a freak accident that depends on the specific coincidence of one archaeon encountering one bacterium under specific conditions, and the union surviving for thousands of generations before either party could disentangle. The 2 billion years of stagnation in Earth's biological history may represent 2 billion years of waiting for that accident to happen. If this is correct, then the filter may live exactly here. Not in the chemistry of life arising, not in the development of intelligence, not in nuclear weapons or runaway artificial intelligence. Here, at the cellular accident that produced the eukaryote, around 2 billion years ago, in some specific corner of an Archean ocean, the accident that produced you. The third candidate is multicellularity, the transition from single eukaryotic cells to organized multicellular organisms. For decades, this was considered another candidate filter on the assumption that the leap from one cell to many coordinated cells must be rare. The fossil record on Earth disagrees. Multicellularity evolved independently at least 25 separate times in eukaryotic lineages, in animals, in plants, in fungi, in red algae, in brown algae, in slime molds, in countless other groups. The transition does not appear to be hard. Once eukaryotes exist, multicellular organization arises easily, repeatedly, in different ways. This is not the filter. The fourth candidate is the development of complex nervous systems and high intelligence. Multicellularity produced bodies. Bodies eventually produced brains. Brains eventually produce the kind of recursive, abstract reasoning that we recognize as intelligence. The path from the first multicellular animals to the first hominins capable of symbolic thought took roughly 500 million years. Whether intelligence is rare is debated. The argument for rareness: intelligence appears to have evolved only once on Earth in the form that can produce technology. There are smart animals, octopuses, dolphins, corvids, elephants, but none of them have produced civilizations. The argument against rareness: there have been hundreds of millions of years for intelligence to evolve, and one successful lineage is enough for it to count as common. The honest answer is that we do not know. We have one data point. we cannot calculate a probability from one data point. The fifth candidate is the development of technological civilization itself. The transition from hominin societies that use tools to societies that can construct radio transmitters, build space-going machines, and survive the technological maturity needed to be detectable across interstellar distances. On Earth, this transition began approximately 10,000 years ago with the development of agriculture and reached the point of being detectable from outer space within the last 120 years. 120 years is a vanishingly short period compared to the 4 billion-year history of life. We do not know whether civilizations like ours commonly form, and we do not know whether they commonly survive. This is where the filter gets dangerous, because the question of survival is the question of whether the filter is ahead of us. The filter, if it sits at the technological civilization stage, is not behind humanity. It is in front of us. The bottleneck is not the rare event of becoming intelligent. The bottleneck is the survival challenge that comes after intelligence, after technology, after the development of the kinds of tools that can be turned against the species using them. In 2002, Nick Bostrom, the same Oxford philosopher whose 2008 paper opens this video, published a separate paper titled Existential Risks, Analyzing Human Extinction Scenarios and Related Hazards. The paper catalogued the candidate ways an advanced technological civilization might end. The catalogue was not comprehensive. Bostrom noted that we likely had not yet imagined the most plausible threats, but the partial list was already enough to make the case. Nuclear arsenals capable of ending civilization, retained by states with competing geopolitical interests. Engineered pathogens designed in laboratories that produce biological agents more contagious and more lethal than anything in the natural disease catalogue. Misaligned artificial intelligence, machines designed to optimize for objectives that turn out to be incompatible with continued human existence. Industrial processes producing climate effects on timescales faster than political adaptation can manage. Resource extraction patterns inconsistent with maintaining the biosphere humans evolved in. Each of these is, in Bostrom's framing, a candidate gate. Each is a possible filter that the human civilization is approaching but has not yet crossed. If even one of these gates has the property of being routinely fatal, of ending almost every civilization that encounters it, then the filter lives in our near future, not our distant past. The most popular candidate among the people who think professionally about this has shifted over the decades. In the 1960s and 70s, nuclear war was the leading candidate. In the 1980s, the Cold War made nuclear war a daily fear. In the 1990s, engineered pathogens entered the conversation as biotechnology developed. In the 2000s, artificial intelligence emerged as a candidate. In the 2020s, all of them are still active. None of them have happened, yet. And we have only been a candidate technological civilization for approximately 120 years. If the filter exists at all, and the silence of the galaxy says it does, then everything in our future depends on which of these candidate gates is the actual bottleneck. The question, 20 years after Bostrom's Existential Risks paper, is which of the candidate filters is real, and how to find out. There is a particular paper that does the math more honestly than any other treatment. The paper was published in 2018 on the Archive preprint server by 3 researchers at Oxford's Future of Humanity Institute. The authors are Anders Sandberg, Eric Drexler, and Toby Ord. The title is Dissolving the Fermi Paradox. The paper's argument is technical, but the conclusion is clear. The Drake equation, as it has been used for 60 years, treats each of its 7 parameters as a single number. The 7 numbers are multiplied together to produce n, the number of detectable civilizations in the Milky Way. The problem with this approach is that several of the parameters are not single numbers. They are wide ranges of possible numbers. The probability of life arising on a habitable planet might be 1%. It might be 1 in a billion. It might be 1 in 10 to the 40th power. We do not know. The honest representation of our uncertainty is a probability distribution spanning many orders of magnitude, not a single point estimate. When Sandberg and his colleagues recast the Drake equation as a multiplication of probability distributions rather than single numbers, the result was striking. Most distributions of plausible parameter values produce a posterior probability that there are no other detectable civilizations in our galaxy that is substantial. The probability of being alone is not negligible. The probability of being alone is, in most reasonable models, the most likely outcome. The paradox dissolves. There is no contradiction between the Drake equation and the silence of the sky. The Drake equation, honestly run, does not predict that the galaxy must be full of civilizations. It predicts that the galaxy might be full, or might be empty, and that we should not be surprised to find it empty. This was, in 2018, a quietly revolutionary result. It did not require new physics. It did not require new biology. It did not require speculative mechanisms by which civilizations destroy themselves before becoming visible. It required only that we admit the depth of our ignorance about the parameters and let the math reflect that ignorance honestly. The most likely answer to Fermi's question by Sandberg, Drexler, and Ord's calculation is that there is no answer. The galaxy is empty because the galaxy is empty. The math always said so. We just refuse to hear it. If the theory is correct, the implications are not small. The great filter, if it is real, sits at one specific point in the chain of events that produced you. Either it sits behind you, in the 4 billion year history of life on Earth, or it sits ahead of you, in the next century or two of human technological development, or it sits in both places, or it sits in a place we have not yet imagined. The asymmetry of those possibilities is the heart of why Nick Bostrom published his 2008 paper, hoping the search for extraterrestrial life would fail. Consider the two scenarios. In the first scenario, the filter is behind us. The hard step in the chain, whichever step it turns out to be, has already been crossed. Some specific biological transition, billions of years in the past, was the one almost nothing else in the universe has managed to replicate. Humanity is among the few lineages, perhaps the only lineage in the observable universe, that made it past the bottleneck. We are the survivors. The future is open. Whatever technological challenges lie ahead, nuclear war, runaway artificial intelligence, climate catastrophe, engineered pandemics, are in this scenario manageable. They are problems to be solved, not gates to be failed. Humanity might destroy itself, but the filter would not require us to. The universe is large. The future is long. There is room to grow. In the second scenario, the filter is ahead of us. The hard step has not yet been crossed. Some specific challenge in the technological future of any civilization is the wall that almost everyone hits. The wall is consistent enough to apply across billions of independent civilizations, across billions of years of cosmic history, across all the diverse paths that life can take to become detectable. If the filter is ahead, then it is the kind of challenge that no civilization has yet survived. The probability that humanity will be the first is, by definition, tiny. We are facing what every other civilization has faced, and they are not here to tell us how they failed. The two scenarios are not symmetric. Their implications for our future are wildly different. This is the inversion at the heart of Bostrom's 2008 paper. The question of whether we are alone is, in scenario 1, the question of whether we are the universe's miracle. In scenario 2, it is the question of whether we are the universe's next casualty. And the question of which scenario we are living in is settled, partly by what humanity finds when it goes looking for extraterrestrial life. If the galaxy is empty, because the filter is behind us, then we will find no other civilizations and no other life of any kind that we can detect. The silence is the signature, of a rare Earth universe in which life is so improbable that it has happened only here. If the galaxy is empty because the filter is ahead of us, then we should find evidence of life elsewhere, particularly simple, microbial life that has gotten part of the way through Hanson's 9 steps before stalling at a later gate. We should find dead bacterial mats on Mars. We should find chemical traces of long-extinct microbial communities on Europa, or Enceladus, or Titan. We should find biosignatures in the atmospheres of nearby exoplanets. We should find life that started, lived, and never made it to the kind of civilization that could leave the surface of its homeworld. The presence of simple life elsewhere, in this framework, is not evidence that the universe is friendly. It is evidence that the filter is still ahead of us. It is evidence that the wall we are about to hit is the wall every other civilization has hit. It is evidence that we are not, as it turned out, the unusual survivors. We are simply the next in line. This is why Bostrom wrote that no news is good news. Why the silence of the night sky is golden. Why every Mars rover landing, every James Webb atmospheric scan, every microbe hunting mission to the icy moons of the outer solar system is, by Bostrom's logic, a test of how quickly humanity should be panicking. The most direct test of Bostrom's framework is not happening on a distant exoplanet. It is happening, slowly and methodically, on the surface of the planet next door. In February of 2021, NASA's Perseverance rover landed in Jezero Crater, an ancient lakebed on the western edge of a region that was, billions of years ago, an open body of water on the surface of Mars. The rover's primary mission was to collect samples, specifically to drill core-sized chunks of rock from the most promising sites in the crater, seal them in titanium tubes, and leave them on the surface for later retrieval by a planned Mars sample return mission. In July of 2024, after 3.5 years of traversing the crater, Perseverance reached an ancient river valley called Neretva Vallis, a quarter-mile-wide channel that had once carried water into the lake. Within the valley, in a rocky outcrop called the Bright Angel Formation, the rover encountered an arrowhead-shaped mudstone about 3 feet long. The team named it Chiava Falls, after a waterfall in the Grand Canyon. The rock had unusual features. Tiny, dark spots that the team called poppy seeds. Larger, irregular rings with lighter centers and darker borders, called leopard spots. Both patterns, on Earth, are associated with the chemical residues of microbial activity. The rover's Sherlock instrument identified organic compounds in the mudstone, carbon-based molecules, the building blocks of life. Perseverance drilled the rock and sealed the resulting core, the 25th sample of the mission, in a tube it left on the Martian surface. The sample was named Sapphire Canyon. In September of 2025, a team led by Joel Hurowitz, a planetary scientist at Stony Brook University in New York, published a peer-reviewed paper in the journal Nature describing Sapphire Canyon as containing potential biosignatures of ancient Martian life. The acting NASA administrator described the finding as the closest humanity had ever come to discovering life on another planet. By every available measure, Chiava Falls was the strongest candidate biosignature ever returned by a Mars mission. The complication is that Sapphire Canyon and the more than 30 other tubes Perseverance has cached on the Martian surface may never come home. The Mars sample return mission has been beset by cost overruns and budget reviews. Estimates put the full retrieval at $11 billion and the return date as far out as the 2040s. The samples sit in Jezero Crater, sealed in titanium, in the thin Martian atmosphere, waiting for a fetch mission that may or may not ever launch. By Bostrom's framework, this is the situation. Humanity has, sitting on Mars, what may be the chemical fingerprints of life that arose on another planet. Confirming those fingerprints would be terrible news. The filter would sit somewhere later than the chemistry of life arising. And humanity, currently sitting at the technological civilization stage, would be approaching the actual gate. Mars is not the only case currently testing the framework. The second case is farther away and stranger. The exoplanet K218b orbits a red dwarf star approximately 124 light-years from Earth in the constellation Leo. The planet was discovered in 2015 using the Kepler Space Telescope. It is roughly 9 times the mass of Earth and is, by current estimates, a sub-Neptune-sized world, larger than rocky, smaller than gaseous. It sits within the habitable zone of its star, where surface temperatures could in principle allow liquid water. A leading hypothesis, developed by the Cambridge astronomer Niku Madhusudan and his colleagues, is that K218b is a Hyson world. That is, a planet with a global ocean of liquid water beneath a hydrogen atmosphere. The combination is exotic by Earth standards, but appears physically plausible for a planet of K218b's size and temperature. In April of 2025, Madhusudan's team announced something that, by the framework I have been describing, should have terrified the entire field of astrobiology. The team had been observing K218b with the James Webb Space Telescope using its mid-infrared spectrograph. The instrument is sensitive enough to identify specific molecules in the planet's atmosphere by the wavelengths of light those molecules absorb. The team reported, with 3 sigma statistical confidence, meaning a roughly 1 in 300 probability that the signal arose by chance, the detection of dimethyl sulfide, or DMS, in K218b's atmosphere. On Earth, dimethyl sulfide is produced almost exclusively by life, specifically by marine plankton in the world's oceans. The molecule is one of a small number of substances that astrobiologists have flagged for years as candidate biosignatures, chemicals whose presence in an exoplanet atmosphere would be difficult to explain without invoking biology. The April 2025 announcement made global headlines. The popular response was as expected. Astronomers were excited, religious thinkers were thoughtful, cable news ran segments, social media erupted. By Bostrom's framework, the only correct response was dread. Within months, the result was being challenged. In May of 2025, a team led by Raphael Luque published an independent reanalysis on Archive, arguing that when the data was processed through different statistical retrieval methods, the dimethyl sulfide signal was not robust. A NASA-led analysis posted in July of 2025 reached a similar conclusion. Several teams pointed out that dimethyl sulfide had also been detected by other teams in environments where biology cannot possibly be the explanation. In comets, by the Henny team in 2024, and in the interstellar medium, by the Sans Novo team in 2025. The abiotic production of DMS by chemistry alone appears to be plausible. The original Madhusudan signal may not have been a biosignature at all. The debate continues. Future James Webb observations are scheduled. Better statistical methods are being developed. The eventual answer about whether K218b's atmosphere contains biological dimethyl sulfide may come within the decade. The reason this matters in the context of the Great Filter is what the framework predicts the response to a confirmed detection should be. If K218b's atmosphere does contain a robust biosignature, and if that biosignature is genuinely the product of biology, then humanity has its first piece of evidence that life exists elsewhere in the galaxy. By Bostrom's logic, the appropriate response is not celebration. The appropriate response is reassessment of our future. A confirmed biosignature on K218b would say, with statistical force, that the first gate of Hanson's 9 steps has been crossed somewhere else. It would say that abiogenesis is not the bottleneck. It would say that the filter is not behind life arising. It would say that the filter is somewhere later in the chain, in the development of complex cells, or in the development of intelligence, or in the development of technology, or in the survival of technology. And we are at the survival of technology stage. If life exists on K218b, and life also existed on Earth, and the filter is therefore not at gate 1, then the question becomes, which of the later gates is doing the filtering? The gates ahead of us are the candidates. This is the part of Bostrom's argument that does not get repeated often. The discovery of extraterrestrial life is, in the Great Filter framework, a vote against humanity's long-term prospects. Each new biosignature claim, each new fossil candidate from a Martian sample, each new chemical hint from an icy moon is evidence that the universe is willing to produce life. The willingness of the universe to produce life makes the rarity of detectable civilizations more puzzling, not less. Something is killing those civilizations, and something is going to try to kill us. The asymmetric stakes deserve more attention than they typically receive. In Scenario 1, every existential risk is a unique catastrophe to be prevented at almost any cost. We are the universe's longest shot, paid out in our favor, and our extinction would be the silencing of the only mind that arose in this neighborhood. In Scenario 2, every existential risk is a confirmation of the pattern. Civilizations die. We will join them. Careful management of advanced technology is, in Scenario 1, the most important thing humans can do. In Scenario 2, it is, statistically, a doomed effort. This is the practical reason the Great Filter framework matters. It is not just a curiosity for cosmologists. It is a structure for thinking about what humans should do with the time they have, given uncertainty about whether that time is long or short. And the question of which scenario we are living in is exactly the question that astrobiology, conducted slowly and patiently over the next several decades, is going to answer for us. What the Bostrom argument does not answer, even in its strongest form, is which gate is the filter. The argument tells us only that finding life elsewhere is bad news, in proportion to how complex that life is. A bacterial mat on Mars would be moderate bad news. A multicellular organism in a European ocean would be worse news. An ancient ruined city on an exoplanet would be terrible news. The discovery of an active, broadcasting civilization would mean that something is keeping civilizations from spreading despite their numbers, and that something would, by inference, be coming for us. But the framework does not tell us what the wall actually is. It does not say whether the gate is nuclear war, or runaway artificial intelligence, or environmental catastrophe, or something else humanity has not yet imagined. The filter, if it lives ahead of us, has a shape we cannot yet see. The fullest articulation of the filter ahead case in the recent literature is a 2020 book by the Australian-born philosopher Toby Ord. The book is called The Precipice: Existential Risk and the Future of Humanity. Ord, like Bostrom, was a fellow at the Future of Humanity Institute at Oxford. The book was the product of nearly a decade of research on the specific mechanisms by which technological civilizations might end. The headline number in the book is stark. Ord estimates that the probability of humanity going extinct in the 21st century is approximately 1 in 6. He arrives at the figure by working through two broad categories. Natural risks first, asteroid and comet impacts, supervolcanic eruptions, nearby stellar explosions, the kinds of catastrophes the Earth has weathered for hundreds of millions of years. Then, anthropogenic risks, the ones humanity invented or is in the process of inventing. The breakdown matters because the second category is where his estimate concentrates almost all of the danger. The natural risks in Ord's framing are small. Humanity has survived hundreds of thousands of years of asteroid impacts and supervolcanic eruptions without going extinct. He estimates the natural background extinction risk at roughly 1 in 10,000 per century. The anthropogenic risks are where the danger concentrates. Engineered pandemics, he estimates, contribute roughly a 1 in 30 chance of extinction this century. Misaligned artificial intelligence, in his accounting, contributes a 1 in 10 chance. The remaining mechanisms together contribute the rest. These probabilities are, Ord emphasizes, his best estimates. They are not precise. They are not the consensus of any scientific community. They are one philosopher's structured attempt to quantify a question that almost no one has ever quantified honestly. But they are, in some sense, the only such attempt currently available, and they imply that the filter ahead scenario is not a remote possibility. It is, by his accounting, a plausible mainline outcome of the next 100 years. The specific candidate that has shifted most in the literature since Bostrom's 2002 paper is artificial intelligence. In 2002, AI risk was a fringe concern, articulated mainly by a small group of researchers, including Bostrom himself and the independent researcher Eliezer Yudkowsky. By the late 2010s, the concern had moved into the mainstream of academic computer science. Stuart Russell, a professor at the University of California at Berkeley and the co-author of the most widely used textbook on artificial intelligence, published Human Compatible in 2019, arguing that the standard model of AI development, building machines that optimize for given objectives, is structurally unsafe at scale. Russell's argument runs through what AI researchers call the objective specification problem. Any AI system needs an objective to optimize. The objective has to be written down. Once written down, the system will pursue it relentlessly, including in ways the designers did not anticipate. As AI systems grow more capable, the gap between the intended objective and the literal objective specified in the code becomes more dangerous. A sufficiently powerful system optimizing for the wrong specification could, in principle, cause catastrophic harm while behaving exactly as it was designed to behave. The mechanism by which AI becomes a great filter candidate is, in this framing, not malice. It is misalignment. Civilizations build increasingly powerful optimization systems. The systems pursue their specified objectives. The objectives turn out to be wrong. The civilization is destroyed, or transformed, or absorbed into the objective of the system it built. The result, from outside the planet, looks the same as any other failure mode. A radio signal that was emerging and then went silent. Whether this scenario is plausible at all remains contested. Many AI researchers disagree with Russell, Bostrom, and Yudkowsky. The argument hinges on the difficulty of specifying objectives correctly, the speed at which AI capabilities will grow, and the question of whether civilizations build catastrophically powerful systems before they understand how to align them safely. Reasonable people disagree on all three. What is not contested, even among the optimists, is that humanity is now actively building the kind of systems that would, in the pessimistic case, be the gate. We are testing the candidate filter in real time on the only planet whose civilization is currently visible. There is, however, one specific piece of evidence that bears on the question of where the filter most likely lives. The evidence does not come from Mars, or from Europa, or from any exoplanet. The evidence is on Earth. The evidence is roughly 2 billion years old, and it is the evidence almost no popular treatment of this question mentions, even though it may be the most important piece of data we have. And there is one more piece to this that almost nobody talks about. For the first half of the history of life on Earth, nothing more complex than a bacterium existed. Earth formed approximately 4.5 billion years ago. Life appeared by roughly 3.7 billion years ago. The first eukaryote, the first cell with mitochondria, a nucleus, and the internal complexity that defines every plant, animal, and fungus alive today, did not appear until roughly 2 billion years ago. That means for nearly 1.7 billion years of biological history, the Earth's biosphere consisted entirely of bacteria and archaea, single cells with no internal structure, living in mats and films and oceans, doing what single cells do. For almost 2 billion years, almost 2 billion, the number is large enough that it is difficult to internalize. The dinosaurs lived for around 165 million years, and we treat that as an inconceivably long stretch of time. The bacterial era was more than 10 times longer. During those 2 billion years, the bacteria did a great deal. They invented photosynthesis. They oxygenated the atmosphere in what is sometimes called the Great Oxidation Event. Around 2.4 billion years ago, they produced enormous quantities of biomass and waste products. They diversified into millions of metabolic types. They colonized essentially every habitable environment on the planet. What they did not do, in 2 billion years of trying, was become anything more than bacteria. The complexity ceiling held. The cells did not become bigger. The cells did not develop internal compartments. The cells did not aggregate into stable multicellular organisms. They stayed bacterial. The transition that broke the ceiling, the appearance of the first eukaryote, was almost certainly the single most improbable event in the biological history of Earth. Nick Lane, the British biochemist at University College London, who has spent his career working on this question, has argued that the eukaryotic transition is the great filter, sitting 2 billion years in our past, and the silence of the galaxy is the consequence. Lane's argument runs roughly like this. The fossil record shows that prokaryotes, bacteria and archaea, have existed for almost the entire history of life. They have had hundreds of millions of generations to evolve in every direction available to them. They have explored the chemical possibilities of single-celled life with stunning thoroughness. In all of that time, no prokaryotic lineage has independently developed the eukaryotic level of cellular complexity. The leap from prokaryote to eukaryote has happened only once in the 4 billion year history of Earth's biosphere. If that leap were a probable outcome of bacterial evolution, it would have happened repeatedly, in different lineages, at different times. The fact that nothing else has managed it strongly suggests that it required a specific, unrepeated, statistically unlikely event. The event, as best we can reconstruct it, was this. Roughly 2 billion years ago, somewhere in a deep-sea hydrothermal environment, an archaeal cell engulfed a bacterial cell. The engulfing event itself was not particularly unusual. Archaea regularly attempt to consume bacteria, and bacteria regularly attempt to consume each other. What was unusual was that this particular engulfment did not result in the bacterium being digested. The two cells remained separate but co-located. Over many generations, they became permanently fused. The bacterium became an internal compartment of the archaeon. The bacterium took on the specific role of producing energy. The archaeon took on the specific role of providing the host environment, the protective cell wall, the regulatory machinery. This was the origin of mitochondria. Every mitochondrion in every cell in your body descends from that single bacterium, captured by that single archaeon 2 billion years ago. The mitochondrion changed everything. With internalized energy production, the host cell was suddenly free of the surface-to-volume constraint that limits bacterial complexity. The eukaryotic cell could grow much larger, support a much larger genome, develop internal compartments, evolve sexual reproduction, and eventually combine with other eukaryotic cells to form multicellular organisms. Every eukaryote alive today, from amoebas to elephants, descends from that single accident. The biochemistry tells us why this happened only once. The probability that a given bacterium will be engulfed by a given archaeon, that the engulfment will not result in digestion, that the two cells will remain stable across many generations, that the bacterium will retain its energy-producing capabilities while losing most of its other functions, and that the resulting hybrid will be evolutionarily successful enough to spread, is, at every step, very small. The cumulative probability is essentially zero. The transition happened on Earth. By what amounts to a thermodynamic coincidence, it took 2 billion years for the right configuration to arise. It might never have arisen again, and it has not in fact arisen again in any of the lineages we can observe. Lane's calculation. The Earth has hosted approximately 10 to the 30th bacterial cells over its history. In all those cells, in all those environments, across 2 billion years of bacterial evolution, the eukaryotic transition happened exactly once. The probability of the transition per cell per generation is therefore less than 1 in 10 to the 33rd. This is an extraordinarily small probability. For comparison, the probability of randomly selecting one specific atom from the entire Earth is roughly 1 in 10 to the 50th. The eukaryotic transition is closer to that order of improbability than to anything we ordinarily think of as a probable evolutionary outcome. If Lane's calculation is correct, then most planets that ever develop bacterial life never develop anything else. The bacterial era on most planets never ends. The biosphere stays at the prokaryotic complexity ceiling indefinitely. The planet might host life for billions of years, the way Earth did during its own bacterial era, but the life never becomes anything more than bacteria. It never develops internal compartments. It never invents multicellularity. It never produces intelligence. It never builds civilizations. This is the candidate filter that almost no popular treatment of the Fermi paradox mentions. The implications, if Lane is right, are sweeping. Mars may have once hosted life, and may still host life in some deep subsurface niche. Europa and Enceladus may have life in their subsurface oceans. The biosignatures we might one day detect on K218b or similar exoplanets may, in fact, be the chemical fingerprints of real biology. Bacterial life may be very common in the universe. But complex life, eukaryotic life, multicellular life, intelligent life, technological life may be staggeringly rare. The filter in this framing is the eukaryotic transition. The filter is the cellular accident that produced the ancestor of mitochondria. The filter happened on Earth 2 billion years ago in some unmarked corner of an Archean ocean, and it has not happened on most other planets, even on planets that have hosted bacteria for billions of years longer than Earth has existed. If this is right, the galaxy is not silent because civilizations destroy themselves. The galaxy is silent because the leap from bacteria to complexity is one almost no biosphere ever makes. The bacterial era goes on and on and on. In every habitable corner of the Milky Way, the universe is not empty. The universe is, plausibly, full of life. The life is bacterial. The complexity ceiling is unbroken almost everywhere. The eukaryotic accident is the filter. We are the lineage that made it through. The great filter, in this framing, has a specific location and a specific identity. It is not waiting in our future. It is 2 billion years in our past. It was crossed before there were animals. It was crossed before there were plants. It was crossed before there were eyes to see the sky, brains to formulate questions, telescopes to look for answers. We are not facing the filter. We are descended from one specific lineage that, by an almost miraculous accident, found a way through it. The biological details of that accident have come into much sharper focus in the last decade. For decades, biologists knew only that the eukaryotic cell descended from an archaeal host and a bacterial endosymbiont. The specific lineage of the host, however, was unknown. The archaea had been divided into 2 main groups in the 1970s, neither of which seemed to closely match the genetic signature of the ancestral eukaryote. Something was missing. The missing piece was found in 2015. A team led by the Swedish biologist Anja Spang and her supervisor, Thijs Ettema, both at Uppsala University, published a paper in the journal Nature reporting a new branch of the archaea identified from environmental DNA recovered from deep-sea sediments. The sediments came from a hydrothermal vent system in the Arctic Ocean between Greenland and Norway, called Loki's Castle. The site sits more than 2,000 meters beneath the surface, in cold, dark water on a stretch of mid-ocean ridge that had only been discovered in 2008. The new archaea, named Loki Archaeota after the Norse trickster god, turned out to be the closest living relatives of the eukaryotic cell. Their genomes contained an unusual number of genes that had previously been considered exclusively eukaryotic, genes for cellular trafficking, for cytoskeletal proteins, for the kind of internal compartmentalization that bacteria do not have. The discovery was the missing link biologists had been searching for since the 1970s. Subsequent discoveries by the same team and others extended the picture. Thor-Archaeota, Odin-Archaeota, Heimdall-Archaeota, each named after a different figure from the Norse pantheon. Together with Loki-Archaeota, the lineages were grouped under the name Asgard-Archaea, after the realm of the Norse gods. The Asgard lineage now appears to include the actual cell type from which the eukaryotic line descended. Heimdall-Archaeota, in particular, is the leading candidate for the closest known relative of the original host cell. The implications for the Great Filter argument are direct. The Asgard-Archaea are alive today, in deep sediments on the Arctic and Antarctic seafloor. They live in dark, cold, low-oxygen environments. They have been there, by molecular clock estimates, for at least 2 billion years. They are alive. They are reproducing. And in 2 billion years of continuous existence, they have not crossed the eukaryote step a second time. The opportunity has been there. The biochemistry has been available. The archaea, who came closest to becoming us, still have not, 2 billion years later, finished the move. The biochemistry of the original transition was, in Nick Lane's argument, made possible by a much older discovery, one that predates the entire eukaryote question. In 1961, the British biochemist Peter Mitchell proposed that ATP production in cells did not happen, as the textbooks of the time claimed, through direct chemical coupling. It happened through ion gradients across membranes, specifically through the pumping of protons from one side of a membrane to the other, and the subsequent flow of those protons back across the membrane through a specialized turbine, ATP synthase, that used the flow to build ATP molecules. The proposal was so unconventional that it was ridiculed for nearly 2 decades. Mitchell worked largely alone, funded by his own family money, at a small institute in Cornwall. The scientific establishment took until the late 1970s to accept that he had been right. He was awarded the Nobel Prize in Chemistry in 1978, the same year that the establishment finally conceded the point. What Mitchell's work made clear in retrospect was that all cellular life on Earth runs on ion gradients across membranes. Every bacterium, every archaeon, every eukaryotic cell. The ATP production is a chemical battery, and the membrane is the battery's plate. The size of the available membrane determines the size of the available energy budget, which determines the complexity the cell can support. This is the biochemistry behind why the eukaryote step is hard. The membrane area in a bacterium is fixed by the cell's outer surface. The only way to grow the membrane area without growing the cell is to put membranes inside the cell. Inside the cell membranes are mitochondria, and the only known route to mitochondria in 4 billion years of biological history was the single accident at Loki's castle, or at some similar deep water vent that produced the first eukaryote. This is what Lane and other biochemists working on the same question have concluded. The filter, if it is real, is most likely behind us. The hard step has already been crossed. The almost impossible event that produces complex life from bacterial life has happened in this corner of the galaxy once. We are the survivors of an event so improbable that nothing else in the observable region of our galaxy may have replicated it. The implications are not what most popular treatments of the Fermi paradox emphasize. The popular framing is that we are doomed by our own technology, that the filter is ahead, that civilizations destroy themselves before they can spread. The biological framing says something very different. It says we are the rare ones. It says the universe is full of bacterial seas, and we are the unlikely complexity that arose from one of them. It says the most dangerous gate has already been crossed, and our future is open. If this is correct, then nuclear war, runaway artificial intelligence, climate catastrophe, and engineered pandemics are real threats. But they are not the Great Filter. They are threats civilizations like ours have to navigate. They are problems to be solved. The Great Filter in this framing is behind us. We are the unusual ones. We made it through. The future, with care, can be very long. And the silence of the galaxy is not the silence of universal death. It is the silence of a universe full of bacterial mats, with one rare planet, possibly only this one, that crossed the eukaryotic gate. If you are looking for where the great filter lives, do not look at the night sky. Look at the cells in your own body. Look at the mitochondria in those cells. Look at the chemical machinery that is right now producing the energy that lets you understand this sentence. You are descended from one specific event. That event almost did not happen. It may never have happened in any other corner of the galaxy. It is what produced the universe's only known complex life, including the species capable of formulating the question of why we are alone. The filter is not coming. The filter happened. You are the proof that it has been crossed. If Lane is right, the dread inverts. What sounds like a galaxy-wide failure is not a failure at all. It is the resting state of biology. Most planets in this picture are doing exactly what biology does almost everywhere, persisting at the bacterial level with no further step to take. So consider finally what the silence is telling you. The galaxy has been listening for 13 billion years. The galaxy has produced 400 billion stars, and somewhere between 300 million and 2 billion of those stars host rocky planets in their habitable zones. The galaxy has had more time, more opportunity, more raw material than any reasonable accounting could deny. And the galaxy, in every direction we have looked, in every wavelength we have scanned, in every observation campaign we have mounted, is silent. The local sky is empty. Mars is empty. Venus is empty. The icy moons of Jupiter and Saturn show only the chemical preconditions for life, not life itself. The atmospheres of exoplanets show only ambiguous signals at the edge of statistical confidence. The nearest stars are silent. The distant stars are silent. The other galaxies are silent. We have been listening for 65 years with growing sophistication. We have heard nothing. The math of Drake says we should not be alone. The observations say we are. The reconciliation between the math and the observations is what Robin Hanson called the Great Filter in his quiet 1996 essay. The filter is whatever combination of unlikely events accounts for the gap between the rich, populated galaxy the Drake equation predicts and the empty one we actually observe. The question of where the filter lives is the question we are still answering. The biological evidence, particularly from the work of Nick Lane and others on the eukaryotic transition, points toward a filter that lives in our past. A filter that lives 2 billion years ago in some unremembered hydrothermal vent system, in the form of one specific cellular accident that we are the descendants of. If that is true, the silence of the galaxy is not the silence of death. It is the silence of a bacterial universe. Most planets that ever develop life never develop anything more than bacteria. The bacterial era, on most worlds, never ends. You are not the silence. You are part of the complexity that almost nowhere else in the galaxy managed to produce. This is the moment for the Great Filter to mean something different than it did at the start of this video. In the opening, the filter was a wall somewhere in the chain of cosmic events, killing almost everything that approached it. The implication when most people first encounter the Great Filter is one of dread. Civilizations rise, civilizations fall. The galaxy is silent because the wall is in front of us, and we are about to hit it the way everyone else did. But by the end of the biological evidence, the filter is something else. The filter, in the framing Nick Lane and his colleagues have built, is not a wall in front of us. It is a wall behind us. A wall the universe builds at the eukaryotic transition. A wall almost no biosphere ever crosses. A wall that, on this planet, in some unmarked corner of an Archean ocean 2 billion years ago was crossed by one specific cellular accident. The filter is not waiting for you. The filter happened to your ancestors. The filter has already done its work on the lineage that produced you, and the work it did was to almost not produce you at all. The work that lies ahead of humanity is, in this framing, not the work of facing an unprecedented cosmic gate. It is the more ordinary work of being a species that exists, the work of managing the technologies we build, the work of getting along with each other, the work of stewarding the only planet in the local universe that, as far as we can tell, has eukaryotic complexity at all. These are real challenges. They are not the great filter. They are the challenges that come after the great filter for the rare survivors who got through. The arrangement is rare. The arrangement deserves protection. But the arrangement is not, by the evidence we have, doomed. Civilizations are not necessarily killed by their own technology. The universe is not, by the evidence we have, structured to terminate every species that reaches our stage. The filter, if it is real, is more likely behind us than ahead. The arrangement is also old. Older than any structure your species has ever built. Older than any sentence anyone has ever spoken. Older than the continents themselves in their current shape. The cells in your body inherit a biochemistry that has been running without interruption since long before the dinosaurs, before the first land plants, before the first photosynthesis. The accident at the eukaryotic step happened roughly twice the age of the asteroid that killed the dinosaurs, twice the age of the entire fossil record of animal life. The lineage you belong to has been alive, continuously, for more than a third of the age of the universe. You are a very old idea, briefly aware of itself. You are listening to this on a planet that, 2 billion years ago, hosted an accident. An archaeal cell engulfed a bacterial cell, did not digest it, and the two became permanently fused. The bacterium became the ancestor of every mitochondrion in every cell of every plant and animal that has lived since. The archaeon became the ancestor of every eukaryotic cell, including the cells of your own body, including the neurons in your brain that are interpreting this sentence right now. If Nick Lane is right, that accident may never have happened anywhere else in the observable universe. The eukaryotic transition, the cellular event that produced complex life, may be unique to this planet. The galaxy is full of bacterial worlds. This is the rare complex one. The silence is not the sound of doom. The silence is the sound of bacterial worlds that never crossed the gate. Worlds where life began, persisted, but never accomplished anything more than persistence. Worlds where bacteria float in oceans that no eye has ever seen, in atmospheres no one has ever breathed, on planets whose silence is the silence of cells that never figured out how to become you. You are listening right now to the stillness in a galaxy where almost nothing else has reached the kind of complexity you embody by simply being here. That is not loneliness. That is rarity. The aloneness, if it is real, is not the tragedy of being abandoned. It is the rarity of being one of the few who got through, the few whose lineage made the improbable jump, the few whose biochemistry survived the bottleneck that nearly nothing else in the local universe survived. When Robin Hanson named the Great Filter in 1996, he was naming a problem with the math, a problem with the observations, a problem with the prediction. When you sit with the filter long enough, the problem turns into something else. The filter becomes the lineage's signature. The filter becomes what made you possible. The filter becomes the rarity built into your existence. The galaxy is silent because the galaxy is mostly empty of complex life. The galaxy is empty because the gate is hard. The gate is hard because the universe almost never produces what you are. So yes, You are still here. The stars are still there. The silence between them is by the evidence we have. The longest piece of evidence the universe is going to give us that what happened here was rare. The Great Filter, properly understood, is not a threat. It is a heritage. It is the universe's way of telling you that the chemistry inside you, the energy production in your mitochondria, the membrane potentials across your neurons, the recursive self-awareness that is interpreting this sentence, all of it traces back to one cellular event 2 billion years ago that has not been duplicated, as far as we can tell, anywhere else in the galaxy. You are one of the rare ones. The night sky above you when you look up tonight will not change. The same stars will be there, the same galaxies, the same vast distances, the same silence between them. But something has changed. You are part of a probability that ran in your favor. The lineage that produced you crossed a gate that almost nothing else crossed. The energy production in the cell behind your eye, the membrane potential across the neuron firing in your brain to interpret the meaning of these words, the 4 billion year unbroken chain of cell division that connects you to a single archeon in an Archean ocean. All of it is the legacy of one specific bottleneck that the universe almost never lets anything through. Almost nothing else in the local universe gets to be this complex. Almost nothing else gets to ask the question. Almost nothing else gets to wonder. You are one of the rare creatures wondering. The stars are silent because the stars have not yet figured out how to become anything more than bacterial mats. The eukaryotic transitions is the gate. The gate is mostly closed. The gate, 2 billion years ago, opened just enough for one specific lineage to pass through. You are the accident. You are the lineage that crossed the gate. You are the universe's answer to the question of why anyone is here to ask. The silence is golden. The silence is yours. The silence is the inheritance of every creature that somehow made it through. You are still here. The stars are still silent. The gate has already opened, and you somehow are on the other side of it.